So, we already discussed the basic fundamentals of resistance and its overall concepts. Now, let's move forward to the more technical aspect parts, wherein we will discuss the two different kinds of laws, which is very, very important on computing overall resistance. Okay, first we need to discuss the two types of laws, which is the Kirchhoff's laws. So the first law is the Kirchhoff's current law. This is also called, in terms of abbreviation, as KCL. No? So KCL is the algebraic sum of all of the currents that is entering a load, which is when they are summed, or you add all of the currents, it must have an answer of 0. Mathematically, the equation for the Kirchhoff's current law is the summation of all of the currents entering a node or leaving a node must be equal to 0 from a counter of n is equal to 1 up to n, which is the number of branches. Okay, to understand this further, okay, we can have here a node. Node is a point or interconnection of all of the branches. And then, for example, we have this scenario. Okay, this is your n node. And then, for example, this is I1, this is I2, this is I3, and this is I4. Okay, to represent this mathematical equation here, okay, so it will depend on the arrow sign. So when you say current entering, the arrowheads must enter the node. And if you're considering current leaving, the arrowheads must be leaving the node. Okay, so in this example, we can have I1 entering first. Okay, I1 this one plus I2 plus I3. Okay, simply equal to the current that will leave the node, which is equal to I4. So basically, this can be interpreted much further if we have a circuit. Okay, this is an example of a circuit here. So we have a battery source, I could say V. And then we have these independent sources. Okay, it must be independent. So it is interpreted here, or represented rather, by a circle with a direction arrow sign. Okay, now since you have a minus and plus of the battery here, which minus here represents the ground, and the larger or the much bigger line here, which represents as a positive sign. So the current will be in an upward direction from negative to positive. So I could say that is IT. Okay, our main goal here is to get IT, and we need to apply the Kirchhoff's current law. So this is the common node, I could say. So this is the common node, wherein all of the currents will eventually go to that node and it will be equal to 0 based from the Kirchhoff's current law. So if we compute that, therefore, okay, current entering is IT, current entering here is I1, and current entering at this node, N, I could say, is I3. So IT plus I1 plus I3. Simply equal to this entering and equal to the current that is leaving on the node, which is I2. So if we compute for the total current, that is simply equal to IT is equal to I2 minus I1 minus I3. And then if you want to get, okay, for example, the total voltage, okay, that will be equal to IT times whatever the total resistance is. So we will discuss total resistance in terms of parallel or series, okay, on the next few slides. Okay, by the way, I forgot to mention here, okay, that KCL or Kirchhoff current law is applied on a parallel circuit which has different branches. So this is a branch, okay? And this is your current source, also another branch. So when you say parallel, they have the same terminal points. So when you say terminal points, this is the terminal points for the positive and the terminal points for the negative at the bottom side. Negative, the positive. Okay, we will discuss Kirchhoff's voltage law on the next slide. Okay, let's continue our discussion on Kirchhoff's law. And our second law is the Kirchhoff's voltage law. So what's the difference between Kirchhoff's voltage law and current law? Well, Kirchhoff's current law concentrates on current. Kirchhoff's voltage law concentrates on voltage. But the connection for Kirchhoff's voltage law is in series. Okay, we will discuss this further on our next few slides. So let us define what is Kirchhoff's voltage law. By the way, the acronym here is KVL. Please take note, this is in terms of series connection. Okay, KVL states that all of the algebraic sum of all of the voltages around a certain loop. Certain loop is a closed path. When you say closed path, a loop must have a voltage, conductor resistances, and load so that you will have a current. Because if this is not a closed path, the current will be zero. That is an open circuit. But here is a closed path wherein it must have all of the elements of an electrical circuit. It will become equal to zero. So in other words, mathematically, the summation of all of the voltages from the counter n is equal to 1 up to m, the number of elements is equal to 0. And Vm here is the voltage or amp voltage of the element. Okay, to understand this further, I have here a circuit. And please take note, here in this circuit, I assume all of the sign or the polarity. Okay, now this is very important, the polarity. We can assume the polarity, okay, for a certain circuit. And the assumption as well of the conventional loop. The conventional is a clockwise direction or a counterclockwise direction. But typically we use a clockwise direction for a certain loop or a certain circuit. Okay, I also use here a special mnemonic, which is I called FIFO method. FIFO as in first in, first out. It's like a football, soccer, FIFA. Here, we have FIFO method. First in, first out. Okay? Now, we need to dictate the polarity sign. So, the sign here, for this example, so that we can apply KVL, you have minus plus here for the source, plus minus, okay, for the resistances, minus plus here because the shorter line here minus the larger line is positive, and you have plus minus here for the resistance at the last element, which is a drop. So if the current goes here, in a certain resistance, it will have a drop, and the drop convention is plus minus. This is voltage rise, okay, for the battery because that is minus plus. Okay, so the current is very obvious from minus to plus. That is voltage rise, and voltage drop on the conductor side, conductor elements. Okay, if we apply the KVL, the voltages around the loop must be equal to 0. It will depend on the sign, and we use first in. So you have the arrowhead here. If it's coincide with the negative value, so it means, this is the first sign, it is minus, so minus VT. Okay, check. Now, here your resistance has a voltage VR1. So how can you compute for VR1? VR1 can be I times R1 because I is constant around the circuit because that is in series. So that is plus VR1. And then you have plus VR2 here, and then minus here, minus VL, and then plus VR3. So that is equal to 0. All of the summation of all the voltages around these 5 elements must be equal to 0, but must follow a conventional loop and polarity. So therefore, now we can say that total voltage is equal to VR1 plus VR2 minus VL plus VR3. Okay, now since we already have the basic concepts and overview of the KVL and KCL, Our next topic will be resistances or combination of resistances in series and parallel. Thank you.
Hello, good day to all of you. Now we will discuss resistance combinations. You have two types of combinations in terms of resistances. The resistance can be connected in series or in parallel, or you can combine together both worlds. Now we will discuss first the series resistance. Okay, the series resistance is derived from this closed loop here. So we have here the total voltage Vt and the voltages from the elements or individual resistors, which is VR1, VR2, and VR3. And the current, wherein the current here, as you can see, the same with those resistances R1, R2, and R3. Now the question is, what is the characteristic of a series resistance? Okay, first, the current is constant. It's very obvious that the current that is flowing in R1, R2, and R3 are the same. Second, the total voltage Vt is the sum of the individual voltages of the elements. So it means that VR1, VR2, and VR3, which is the voltages of R1, R2, and R3, is simply equal to Vt. So we will derive this one from the last slide using the Kirchhoff's voltage law. And considering again, we follow the polarity marks. Voltage rise, and then voltage drops from the resistors, so that we can arrive at this equation: Vt is equal to VR1 plus VR2 plus VR3. Okay, I already have the pre-derived here of the resistances, that all of the resistances connected in series will be equal to R1 plus R2 plus R3, or simply this is similar to this equation, because we will make use of this equation to derive this equation here. So since we have Vt here is VR1 plus VR2 plus VR3, this is also the same as I times RT equal to I times R1 plus I times R2 plus I times RT, simply because the current that is flowing in R1, R2, and R3 are the same or constant. Hence, the current will cancel out here, leaving behind this equation, which is RT is equal to R1 plus R2 plus R3. Now, if you have many resistors connected in series, okay, you can have plus R to the n. Now, how can you determine if the combination is in series? It's very obvious here, because it's like you have a string of resistances, R1 and R2, R3, and they're connected, okay, in a straightforward path. So it means that if one of the resistors here is being open, the current will be zero. It's like like a Christmas light. Christmas lights is connected in series. If one of the bulbs is busted, or you open one of the bulbs there, which is one resistance, then the other combinations will not light. So it means that when you say resistances connected in series, it's like a Christmas light or a string of resistances connected together. Okay, now we will discuss one parameter that we did not discuss in resistance, but this is the much proper way now to discuss this one, this conductance here. Conductance G is the reciprocal of the resistance. So it means G is equal to 1 all over R. The unit is mho, but accidentally, mho is the palindrome of ohm. Okay, so ohm is also mho. So this is the unit for resistance, ohm, and this is mho. Okay, accidentally, this is the right time to discuss this one. And it's also Siemens, in terms of unit. Okay, so G is equal to 1 over R. So if we apply 1 all over G here, 1 over G1, etc. Now, this is also the combination of the resistances connected in series. 1 over GT equal to 1 G1 plus 1 over G2 plus 1 all over G3. Okay, hello. So, we will tackle now parallel resistances. The second type of resistance combination is if resistances are connected in parallel. Now in our example here, this is an example. Okay, our example that I make use only of two resistances and one voltage source connected along these branches. Now, what are the characteristics of a parallel resistances? The voltages along the branches is the same. So it means when you say parallel, okay, your resistances here are connected on the same polarity mark. So it means this one is negative for this example because this one, the shorter line is negative, the larger line on the battery terminal is positive. So therefore, these are the nodes here, the top and the lower part. So you have plus here and you have minus here. So both resistances are connected in parallel. However, this will be a different case. If you have a resistance R3 here connected, okay, R1 and R2 is not parallel anymore. However, R3 and R2 are in series, so you need to add it up, and then whatever the result here is in parallel now with R1. Okay, for that, this is a perfect parallel combination because there's no resistances in between resistances. So you have R1 and R2 are on the same polarity marks. Okay, another characteristic is the total current is the sum of the individual currents on the branch. So it is derived on your KCL. So if we have a KCL here, that IT and I1 and I2, we can add it up. IT is equal to I1 plus I2. And then, voltage is constant because, as we have mentioned, they are connected in the same branch. Okay, the voltage is in the same polarity mark. Okay, those are the characteristics of the parallel resistance. So let's move forward to the calculation part. So by Ohm's law, we know that E is equal to IR, or V rather, is equal to IR. So we can now get the current here by dividing voltage by the resistance. So IT here is V all over RT, I1, rather this is voltage here, sorry. So I1, V all over R1 plus V all over R2. Now, so you can see voltage is constant, so the voltage will cancel out eventually, and leaving behind our the most important part of the discussion here, the formula for parallel resistance. 1 over RT is equal to 1 over R1 plus 1 over R2. But if you have plenty of resistances or branches after R2, you can have plus 1 all over Rn. So if you have 6 resistances, so 1 over R1 plus 1 over R2 plus 1 over R3 up to R1 over R6. So this is very familiar, looks fun, with the conductance, total conductance formula from our last slide. And hence, if you have only 2 resistances here, so this is a main formula for shortcuts on some of the problems. If you have 2 resistances connected in parallel, so go back here and then use a little bit of algebra. It will eventually yield to RT as product all over the sum. So this is the mnemonic here, product all over the sum of the 2 resistances. Okay, R1 times R2 over R1 plus R2 plus, but please take note that this formula is only for 2 resistances. And for the total conductance, well, if you have the reciprocal of this formula, it will become like this. So as you can see here, this is series. Okay, formula from the last slide. So in terms of GT and RT, they are very obvious. They are reciprocal to each other. If in series, that is connected in parallel, but in parallel is like connected in series for conductance. Now we can now solve some problems regarding resistance combinations in Kirchhoff's law.